Welcome back to the second session on observability of NSO and monitoring of NSO. Here we're going to take a deeper dive into the sort of underlying technology, what that makes progress trace possible, or rather perhaps the export of this to these common off-the-shelves tracing and graphing tools. So we're gonna start by looking at NSO itself and sort of progress trace in NSO, what it does, what it's capable of doing. So I'm gonna switch over here to my console. I'm currently logged into a container that's running NSO, and we can have a brief look at the NCS configuration. So to enable progress trace output, there are two things that you need to do in the NSO configuration itself. So you have all the progress trace configuration inside of NSO is hidden. So that means to be able to unhide that, we have to enable the hide group debug in ncs.conf. And this is how you do that. You just add this hide group name debug and sort of end. And this then enables you to unhide this group. This is then like this, unhide debug. And we can look at the progress trace configuration like this. Okay. There's a second part here to the, let me see if I can find it. It's in the log session somewhere. Should have just searched for this instead. So here we go. All right, sorry. This is gonna be slightly tricky to follow, right? But so in your ncs.conf, there's this logs section, and if we go down here and look at the end, we've added this part. So progress trace enabled. We also set the directory where the progress trace files, if you enable file output, where they'll be stored, and this is the normal NCS log directory. Now, we just looked at the configuration. We can do that again. We open up the CLI, unhide debug, show configuration progress. So all the progress trace configuration is under this progress container. And in here, we've set up a trace called ptrace. The destination is a file, ptrace.csv, and the format is, of course, CSV. It's enabled, and we have a verbosity of very verbose. So if we go into the, for NSO and Docker that we're using here, the logs just end up in /log, right? If you have a normal NSO system installed, they'd be in your run directory, right? So here we have the ptrace.csv, and we can just have a quick look at that. So these are the columns of the CSV file. We have the event type. We talked about this before. So there are start and stop events. There are info events as well. We have the timestamp, duration, session ID, transaction ID, data store, context, subsystem, blah, 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 etc. Right? Message is perhaps one of the more important ones. That's the applying transaction that we see. There's also annotation, which is more for reporting errors if something goes wrong. But this is the basic output of CSV files. And this is very useful, I think, to just output to CSV files. It makes it easy, both in development, CI, as well as production environments, to output to CSV files that you then ship elsewhere for processing, essentially. Before we talk about the other way of getting progress trace, I want to talk about the verbosity level, right? So this is also something that I mentioned in the first part, that verbosity, at least up to this verbosity level of very verbose, the performance implications or overhead of progress trace is pretty much negligible. You don't need to think too much about it. So here, the verbosity levels that we have are normal, verbose, very verbose, and debug. And up to this level of very verbose, the performance impact is essentially not measurable. There have been tests done on this in the system validation CI setup for NSO, where we have tests running over 1,000 seconds, over more than 15 minutes, and we simply couldn't tell the impact of progress trace, because the normal variability, which is a few seconds on these tests, so less than 1%, is still more than the impact of progress trace. So up to this level, I'd say is fine for normal production systems. You can enable this and just leave it running. Whereas the debug level most definitely is not. This is something that you want to do in development environments, maybe in CI, in particular setups where you want to look into some form of detail. It really is. The name says it all. This is for debugging things. I should also mention that the levels, or rather how messages or different events are mapped to these levels, have changed. So what I'm stating here, that the very verbose level is fine for production use, is true for NSO 5.4 and later. In earlier versions, you had a different mapping, and so you should proceed with care. But again, also as I mentioned in the first session, the progress trace format has changed quite a lot with 5.4. So I really would recommend that you start with 5.4 or a later version. Okay, so this, I think, sort of sums up the CSV output that we have. It's also possible, you saw the format here is a, where am I? Set destination format. This is, we can also set a log, which is a pretty printed log. And this is pretty much what goes to the devel log. But for most, at least if we want to programmatically consume this, the CSV file is obviously a better choice. Okay, so CSV is one output for this. Another output that we're using in the opentelemetry-exporter package is to receive these progress trace events over the NSO notification API. So I'm going to switch over here to the code base. So this file is called ptrace.py. I think if we yeah, I have it here. So in the opentelemetry-exporter repository, you have the packages, opentelemetry-exporter, Python, and in there you'll find this ptrace.py file, which is doing most. It has most of the functions for processing the progress trace files. So in here, I am going to come to the notification API. I just want to first sort of talk about the overall structure of what we're doing here. So the processing of progress trace events here is designed as a pipeline of different processing stages that you hook up to each other. All of this is implemented in Python, and we're using Python generators to do this. So you're essentially, you can think of it as a pipeline like this. In this case, we have the CSV reader, so we're able to take these CSV progress trace files as inputs, right? And then we pass that on to a processing stage. In this case, it's called uplift 53. We'll also get to what that is. There's another called transmogrify, right? And finally, we can output that to another CSV file if we want. So this is a sort of processing stage that it looks like. You'd call that in Python like this. So it's sort of chain functions, but the functions here are generators, which is why it becomes more of this sort of pipeline. CSV file, so using the CSV reader, that's one input. The other input that's not visualized here is the notif something, notifs reader. So this is what reads from the notif feeder. It is. So this is what hooks up I cannot navigate my own code. Here we go. Get ptrace notifs. So this is the first thing. This actually hooks up. This is how we do that. We open up a socket and we connect this socket to the NSO notification API, and then we ask for these. Our mask here was headed to the events called notif progress, right? And then we get all the progress trace notifications that we want. We can also see here that it uses as the verbosity level is very verbose, so it sticks to what is okay from a performance overhead standpoint, right? So in NSO, in this setup, we have this package loaded. Maybe it's difficult to see. It's called opentelemetry-exporter, right? So we just load up this NSO package, and that package, when starting up, it will attach to the notification API, consume these events, and then do whatever it's instructed to do with them. And that's the other part of the configuration here under progress. So it augments in this export container. So here we can enable the export, and we have two different types of output. There's the InfluxDB. So here we just export it to the host. It's called InfluxDB, and we can also enable Jaeger output. So this particular package is implemented in a repository that's using the NSO in Docker sort of style of development. So that means it's very simple for us to take this package and similar or support packages that we have around it, like the slow service, for example. That's all in this repository. It's here under test packages, slowness, I think. Take this and build a container out of it, test NSO container that we can use. And so when we start this up, we just ask for test and start, essentially. Well, first you do a make build to build the containers, container images, then you do a test and start. And you will get this environment that we see here. So this is a bunch of different containers that helps us test. What I've shown you so far with Grafana, we have InfluxDB, we have Jaeger. All of those things are part of this test environment. And these are sort of NSO and Docker concepts that we're using. So we can see here all the containers. They're called test and opentelemetry-exporter because that's the package, right? We're currently on NSO 5.4, KLL as my username, and then we have these different containers. So we have the NSO itself. There's Elasticsearch, Kibana, Grafana, Jaeger has a sort of microservices kind of thing. So it has multiple components: Jaeger collector, an agent, the UI called Jaeger query. Then we also have a node exporter for Prometheus and InfluxDB. So all of these things are running, and when we start up this test environment, we get these things, and that's what I think it makes it very easy to work with this. We can run this make target that lists the IP addresses of these systems, and we can immediately use them. And that's also the configuration that we looked at in NSO is currently sort of catering to this environment, right? So when we're exporting to a host called InfluxDB. All of this test environment is connected to a virtual network. So inside of that virtual network, resolving the name InfluxDB will take you to the InfluxDB container. But again, that's localized to this test environment, and is it really a feature sort of NSO and Docker and how that sets things up for us. Okay, so I'm gonna go back, talk a little bit more about the code that we have. So there are the processing pipeline here. The one that we show this is a simplified one, really, to just sort of show how a processing pipeline could look like. At the start of the pipeline is something that feeds the pipeline, right? So either a CSV reader or the notification API reader. After that, we have some processing stages, and I'd say the main one in this entire package is the one that's called transmogrify. And this is a sort of a transformation stage that transforms the data that we get from NSO into something that is more suitable for export to Jaeger, as well as to a time series database, right? I'd say the primary things that it does to the format is it pairs up the start and stop messages of spans. It finds the parent span for something, which is much more difficult than you'd think, actually. But in particular, when you're moving between sort of services and then devices. It also does a couple of different other things in the transmogrifier, but that is really the heart of this entire pipeline, right? There's another big processing stage called Uplift 53. So this wasn't in the original version, but this is something that we added on. It's that sort of upgrade shim. So it takes the format of progress trace as it looked in NSO 5.3 or earlier, although I haven't tried it really with older versions. It takes that format and it changes it to become more of what the format looks like in NSO 5.4. At least it's sort of a best ever thing, because some information is simply lacking, but it does it as best it can. Then, in addition to this, there are various processing stages. Let's see if we can generate. Here we go. So here we have a few of the pipeline things. These are mostly bug fixes. So you can see these fix dev snapshot is a small processing stage that I don't remember exactly, but I think that the message contains something incorrect. Right. So this is yeah. In NSO 5.5 and later, this is already addressed with this ticket, but in earlier ones, the message is incorrect. So we rewrite those messages, right? And that's an example of the kind of things that we do in here. And it's something, I mean, you could call this a bug, right? But some of these things aren't outright bugs. Sort of like this one. Perhaps we didn't know better, but as we worked more with the data, we realized what is a better format. And as we improved it in NSO, we've also done fix-ups in this in here. So it makes it easier to work with older versions, right? So some of these are bug fixes, some of them are sort of improvements to the format, etc. So the actual pipeline is quite long. I don't know, maybe something like 10 stages. At the end of the pipeline, and I mean, remember here that, you know, in Python you have to read this in the sort of reverse order. So stream in here in the middle, this is actually the input, right? Whereas on all these fixes are applied, and then transmogrify, that main transformation stage that I talked about, that's applied at the end here. But this isn't the true end. There are other things happening afterwards. Let's see, where is this? It's all put together. At least here, if you're running it interactively like a CLI utility, which I'll also show in a second, then these things are added at the end, right? So we have our stream, sort of, where's the stream? Here, CSV trace reader. This is where we get the stream from the beginning. We have some extra stages that can read time. We can rewrite the timestamps in there. We can randomize certain things like transaction ID and user session ID in a actually sort of deterministic fashion. Then if we have Jaeger export enabled, we're gonna add the export opentelemetry processor to our pipeline. If we enable InfluxDB export, we're gonna enable export of those. So these are actually 3 different processing stages that export different the data in different formats in Influx. And that is how we put together the entire processing pipeline. Part of why I'm showing this is that if you want to do interesting things with the data, you can actually modify this, right? You can add your own processing stage. If you want to export to another time series database, you could actually do that. It's fairly simple. It's not a lot of, if we go and look at one of these functions here, so export influx span, this function, if I just make the text 2 steps smaller, is in a single page, right? It's 35 lines of code. So pretty much all functions look like this. 4 event and streams. So we're fed this pipeline that we have, the previous stages that are generators, and we iterate over that one. and then we apply some logic, right? So we dig out the data that we need, and then we export this. So to actually look at that export, we're gonna flip over into the user interface so Grafana and Jaeger really to understand the export that we do with influx, so time series style data. All right. So I have here, this is actually, I prepared this before because it's slightly difficult just to sort of recreate the entire setup, right? But so I prepared this, but it's very simple. I ran this, it's the test simple. It's called the fast target, which just executes, I mean, you can see that it just executes a single transaction, or actually two transactions. It cleans up first, and then it creates a slow service. And this time it doesn't actually tell it to sleep or anything. So this will run as fast as possible. And that's the output of that we're seeing here, one of these transactions, right? So what I wanted to show here is the correlation between what this looks like, what a transaction looks like in the tracing output. So we have the Jaeger output here on top, right? And then here at the bottom, I picked out, we can actually look at the, so this is the query, right? Select duration from the span measurements. So this is the query that we do in Grafana to display this, right? And this is what it looks like. So there are actually two exports of time series data happening. And as we see here, or we'll see in the code as well, is that the time series database that we're using here is InfluxDB. It's one. I mean, there are other alternatives out there like Prometheus, but for what we're doing here, we want to be able to save events happening at certain times. Then InfluxDB, which has more of a raw database interface than say Prometheus, is a better choice, right? Because it allows us to insert data points exactly as they happen, rather than Prometheus, which has this sort of polling mode. So all of the trace information is exported to Jaeger, and here into Influx as these spans. And what we see here at the bottom is really sort of the same thing as on the top. So each span is going to be inserted into InfluxDB, but instead of having all this sort of extra information, what we see here is just the duration and the name of the span. And in this particular graph, I'm ignoring the name. I can bring that up in a little while, and you'll see that too. But here we just see the duration. So every span is collected into the time series database when it ends, and the duration value is, of course, the duration of the span. So if we see here the first data point that we have, it says 0.42 milliseconds. So that's the first span that ended. And if we go up and look in our trace here, we see that the first span that ended, not the first span, right? Because these ones at the top are the first spans, but they end at the very end of the transaction, right? But the first one that ended is this one. It's grabbing the transaction log, and it takes 0.42 milliseconds, right? Second one should be this one, creating rollback, 1.94 milliseconds. And if we go down here, we'll see, yeah, this one is 1.94. So this is how these, this is how the data is presented in the time series database versus the Jaeger tracing. We can bring up here, we can change the, if we quickly change the graph type to be a table instead, and we can change the output here, and I'll also add the name column. Then we will see here, oh, this is really quite, right, something like that. So here we can now see the, let me see if I can reload this. Oh wait, and my edits will be discarded. Okay, so but anyway, here you can have you see the table of all these different ones, right? So we start out with the grabbing transaction log, 0.42, creating rollback file, 19 something. Scroll bars are messing up the output here. But this is what the raw data looks like, right? This is the first of two data formats that the output to the time series database. There's another one as well. We can again go in here and change. Let's see. The other one is called transaction, or so I thought. What is it called? Oh, is that? It's called transaction. Oh, right. The field is not duration anymore. So the transaction one sort of outputs things differently. If you imagine the span measurement will have duration as one of the columns, in here we instead sort of pivot our data so that every span has its own column. So the transaction, let's look at that. Let's bring up a few different ones, right? Let's remove the group by. So we can, let's change this back to grabbing transaction lock and what else? Creating rollback file. Let's take these ones for example. So what we see now is that we get the different spans, but they are in their own column, right? And they have the value. It's the same value as before, although I guess it's in nanoseconds instead of milliseconds. So creating the rollback file instead of 1.94, it says 1935 here, right? Grabbing transaction log 415, applying transaction 24804. So that is actually 24.8 milliseconds, right? And that's also what we see here. The entirety of this trace is 24.8 milliseconds. So we have these two different measurements in Influx, and the benefit of this one is that it makes it very easy to see or compute rather various values, right? So if we wanna, we can easily just do a computation here instead, right? So applying transaction or divided by creating rollback file, and this way you can compute the percentage of an operation taking sort of for the entirety of your transaction, right? So that's exactly what we use actually in these other graphs that we have down here, like this one, rollback file creation. If we go in and look at that one, we'll see that it's the max value of creating rollback file divided by the max value of holding transaction log. So during the time that we're holding the transaction log, we compute the percentage, how much of that it takes to create the rollback file. And this is done based on data in this transaction table, right? So that is the benefit of the transaction table. Otherwise, I would say that the span measurement, where each span is exported as individual data points, is more natural. It's just that these time series databases, they're not great at doing this kind of computation. That's why we have this transaction table. Is really sort of out of convenience, right? Because otherwise, the alternative is to express this as two subqueries in InfluxDB, and it becomes sort of messy, right? And as far as the size here, or I think that's actually a bug. It's not supposed to be in nanoseconds. We should have this as milliseconds, but that's a separate. We should address that separately. Yeah, so that is and so per default, the pipeline that we build up in the export will export both of these, right? And right now the only supported time series database is InfluxDB. But it's possible to add support for something else. It's just it's a piece of the code there that you need to export to something else, but it's a fairly small piece. There's another aspect to the OpenTelemetry package. So far we've been using it as an actual package in NSO, but it's also possible to invoke it directly from the command line. We have the ptrace.py file. that hosts our sort of library of processing functions, right? So it's a file that we looked at before. This one you can simply run it as a Python script, right, from your shell. So what we need to do first though is set up a virtual environment. Now let's create that. We activate that one, then activate, and then we install the all the requirements or the dependencies that we have. They are listed here, requirements.txt, and that will probably take a little bit of time to install those things. Okay, fairly fast. Most of it is cached, I suppose, on my machine. Okay, so once that's done, let me also figure out the addresses here to our system. Okay. Then we can run the ptrace.py file. We do --help to get all the arguments. And let's fill in. So we can start with the Jaeger host 172.18.02. I happen to know that the address here is .2. So what we actually have is that we have a Jaeger agent running that collects this data, and the Jaeger agent is running in its own container that we have right here. This is the Jaeger agent, but unlike the other containers, it doesn't have its own network namespace. It actually attaches to the NSO container's namespace. And for that reason, we need to look at the NSO container's IP address, and I happen to know that it's always .2 because it starts up first. So that's .2 for that one. Then we have, let me scroll up here and see, InfluxDB is on .9. So InfluxDB host 172.18.09. We instruct it to export InfluxDB as well as export to the Jaeger system. We need a CSV file, and as part of this package test suite, it comes with a number of CSV files that we can use. So we take this input simple 54.csv, and that's about it. We can run this. It will process the file. I mean, this is a very small file. We can look at it. It looks like this, and then it exports that data. So we can switch over to Jaeger. But actually, so I think if we look here, there's actually no data, and that is because this file, as you can see here, this file is from long ago, and per default we look at the current day. So what we can do together here, we have the normal processing of this file, but we also have some extra options. So read time is one of them, so we can read time the entire file. And that takes a time argument, and there's also rando, which randomly rewrites the transaction ID. So this is nice if you want to sort of replay a file, a CSV file, multiple times, just for sort of working with trace data, etc. Right? This can be useful. So what we're going to do here to have this show up today is that we're going to retime it, and so retiming now says, you know, take the first event in the CSV file, put that at the current timestamp, so right now, and then keep the deltas. So the second event, if that happens 1 second after the first event, that is now going to be the current time plus 1 second, etc., etc. So the relative time within the trace is kept. It's just that the whole thing is sort of shifted, moved back and forth. The retime argument also takes, I mean, now is parsed to being right now, but you could write a date here or something like that if you want to place it at another time. Okay, so let's run that again and switch over to Jaeger, and we're gonna do a refresh. Does this show up? Yes, it does. Okay, there we go. We can do like that and see this whole thing. So this is now the CSV file for that simple 54. I don't know if you can sort of compare in between here, but they align, I'd say. And that is how we can use ptrace.py from the command line, which I think is very, very useful. I mean, in particular for production systems, you might not, at least when you start out, you might not want to set up this entire sort of observability environment, you know, with Jaeger and the time series database in your production setting. So perhaps you want to start with exporting the progress trace data from NSO in a CSV file, and then you take that CSV file and transfer it to another environment for offline processing, and then you would use precisely this sort of environment, right? Okay, so we've seen how we can sort of produce our own graphs in Grafana, and for the next thing, I'd like to have a look at how we can further instrument our code. So I'm gonna open up here. Actually, let's do it like this. What's this? Yeah. So here we go. I think if you've seen this before, right? Open up. Oops. Here, that in this trace where we ran our slow service, there is this span called sleep configured time. This is not one of the spans that are part of standard NSO. So this is something that actually comes from our user code. So inside of the create callback. And this is what it looks like. So this is the normal, I mean, in Python, a service callback for create. And here we're using this context manager called ptrace service. And we just specify in here the name of it, and this becomes the span name. So anything that happens within this context, so well, essentially all of this, right, is going to be captured within the span. So here we can see that what we actually do is time.sleep, and then we take as input the create slowness leaf of this service. In this particular case, look at the graph, this was less than a millisecond because we didn't actually do a sleep here. So the less than a millisecond, 0.92 milliseconds here, that is just sort of overhead in these statements, I suppose. It's probably, you know, reading this leaf, we actually go out to CDB, check what's there, etc. Right? So probably some of these things that take a little bit of time. There's a second one here, and there are actually two different input leaves to this service, so we can ask for a deterministic sleep of a particular time period or duration, and then there is a random create slowness, and so that gives you a random sleep. And if that had been used, if it wasn't 0, then we would see yet another span called nested random sleep. And as you can see here in the code, this is nested within this sleep configured time, and that will also come out nested. So we can do this quickly, right? Go into the CLI, and we do a set slow service test, and we do a random create slowness, 1 second, let's say, and then a normal create slowness as well. You can do 2 seconds, and then we commit. We can do details, and we'll be able to see it both here as well as in Jaeger. So here you can see the sleep configured time, and then we have a nested random sleep in there. And you can see here that does a random sleep within 0 to 1 second, because we give it 1 second as a parameter. And then the sleep configured time takes now 2.584. So it's the 2 seconds plus this, right? But that span encapsulates the whole thing. So that's why you get the sum of it here. And if we back out to Jaeger, we can look at this and see, whoops, let's see here. We can find this one, and we'll see here that they are indeed nested within each other. So this is a way of instrumenting your code further, and the implementing such a context manager can be done fairly easily in Python. So the actual functions that you need to call are report service progress start, so this one, and you call that on the transaction handle that you have here, T, which is NCS magic get trans, and then at the end you have to call stop on this thing. And so this context manager in Python just makes that easier to do. And there's also, this is included in the in this package that is in the opentelemetry-exporter package, so you can just copy the code from there and use in your repository. I want to switch over to Grafana. So this time what we can do, well, as we actually have the graph up here, we can just use this. So if we, what's that span called? Nested random sleep. Nested random sleep. So now we're going to create a graph based on that data, right? And this comes from the span table. And now we need a different time span. Probably that's 5 minutes or so. No? Oh, sorry. Where I got that totally wrong. I was trying to select the the name of that as a, okay, we're still not quite there. Why is that? This should be, oh. So InfluxDB is a little bit particular when it comes to quoting. I usually forget about what we need to do. So it's double quotes for like the measurement name and apparently the column names or tags names in the where clause, whereas actual string values, for example, should be single quote. Okay, anyway, so here we have it, right? I mean, we saw before we ran a single instance of this service we created, and it slept for 580, right? 580 milliseconds, and that's what we're seeing here. So this is how you can instrument your code, and from that create your own graphs, right? Showing whatever it is you want to show. Okay, so I think that's pretty powerful. It's a powerful way of gaining insight into your application. Okay, and with that, I would like to conclude this deep dive into observability and monitoring of NSO. I hope you've gotten a better understanding of how progress trace works in NSO, how you can make use of it together with this opentelemetry-exporter package. This package, its repository, you can find on the NSO developer space on GitLab or GitHub. So in this case, the authoritative repository is on gitlab.com/nso-developer/opentelemetry-exporter, and you'll find this page. In here, this uses an NSO in Docker skeleton. So if you're using NSO in Docker, this will be really quite easy to set up. You do a make, build, and test and start, and you get the entire environment together with containers of Jaeger, etc., up and running for you. If you're not using NSO in Docker, you simply extract the package from the packages directory. You have the opentelemetry-exporter right here. And I hope you've gained an understanding of how you can use this, how you can instrument your own code and create custom graphs in Grafana in order to understand how your application behaves. Thank you very much for listening. And again, if you have feedback, questions, or comments, please do reach out to me. Okay, thank you very much.